Hi, everyone. I'm Alvin. Today, I'm going to be talking about binary search. So let's move forward. Okay, so on the agenda, it's pretty straightforward. We're going to be just talking about, in general, searching. We're going to be just talking about linear search and then go into binary search, like contrast the two. And then we're going to go over 2 example problems, and then we'll head into our contest. And so let's do a little bit of a fast forward into the future. So a little bit into the future, congratulations. You guys are graduating from UCLA. There's just one tiny little problem though. Our Chancellor Jean Block sends an email to all students, all graduating students, saying they're no longer refunding the money left over on Bruin card accounts. So all that money that you deposited into your Bruin card that you just have left over for, like, I don't know, laundry or buying from vending machines, they're just going to take it all if you have any extra. But you're not willing to let that happen. And so you don't want to let the school take any money from you anymore for nothing in return. So you're gonna try and spend all the money in your Bruin card before you graduate and get locked out of your Bruin card account. And so you rush over to the UCLA store, like Bruin Walk, and at the UCLA store, you rush in. You want to make it really quick, so you want to buy the most expensive thing that you can afford at the UCLA store. And UCLA, the store has a lot of different items, ranging from $2 Scotch tape all the way up to like a $2,100 iMac. So there's a wide variety of things that you could buy, but you're just looking for the most expensive thing that you can afford. You have no idea how much money is in your Bruin card, but if you bring an item to the cashier along with your Bruin card, they'll tell you if you can afford it or not. And so how do you find the most expensive thing that you can afford? Do you guys want any time to think about this problem? Or you're already coming up with solutions in your head? Yeah, you have a suggestion? Yeah, good job. That's exactly what binary search is. But let's say, pretend maybe you thought CS wasn't for you, and then you ended up transferring to a different major, like, I don't know, psychobio, something in pre-med business major, and you forgot all your CS knowledge. So maybe the first thing you think of is something that we as CS call linear search. And your search space from left to right. So in this case, you're going to start with the cheapest item that you can buy. You can see if you can, you check with your Bruin card, see if you can afford it. And the answer is yes. So you go to the next cheapest item, which is your Bruin mug. So you do your check again. It's good. Go to the next cheapest item, which is your UCLA cap. Keep going, keep going. Go to the cookbook. Get to the gaming headset. Wow, you have a lot of money on your Bruin card. And then you finally get to a Microsoft Office subscription for 1 year. Can you afford that? Unfortunately, you cannot. You can't get Microsoft Office for a year before you graduate, which is very unfortunate. But so we have essentially found out what the most expensive item we can afford is, which is the gaming headset. So this is a pretty straightforward algorithm, pretty easy to understand. You just start with the cheapest item, check, and then you keep going up until you get something you can afford. And then the one right before that is the most expensive item that you can afford. And so here's like the pseudocode. So you want to repeat with like the elements starting from the first elements. You check if that's what you're looking for. If it is, you stop. Otherwise, you move to the next element. And I'm pretty sure everyone here has coded something like linear search or has done linear search like somewhere in their lives. So this is pretty intuitive. Runtime for linear search is O of n, because if there's n items, you potentially have to do n different checks. So O of n runtime. Unfortunately, that isn't too good for our example, because if there's 1,000 products at the UCLA store, you might have to go up to the cash register and do 1,000 different checks. And let's be honest, that isn't really happening, because if you go up to the cash register and say, hey, this is the 50th time I'm coming up to the cash register for this item, can you check it for me? What do you mean get out? So we need something a little bit more optimized, something faster. And the algorithm that we come up with is, you guys probably already know, binary search, but where exactly does that idea come from? How did we come up with binary search? So suppose that we know that we can afford the headset. What can we say about everything cheaper than the headset? So if we can afford like the $60, we know there's at least $60 in our brain card. What can we say about all? Yeah. Yep, correct. So if we can afford the headset, then we can afford everything cheaper than the headset. And then the other way around, what if we can't afford the headset? What can we say about everything more expensive than the headset? Basically the same answer, right? I don't think you're gonna have to go through that. If we can't afford the headset, then we can't afford anything more expensive than it. And then from these two observations, we can come up with a really efficient algorithm for searching through an ordered list, and we will call that binary search. Okay. And in binary search, the idea of the algorithm is essentially divide and conquer, and you want to reduce your search area by half each time. And so we're going to start off with a search space that is our entire like store. Let's just assume that this is the entire store for now. And then we want to go to the approximate middle, or somewhere close to the middle. For this, it's going to be the cookbook. We do our little check, and then we should get a yes, we can afford the cookbook. And so now we reduce our search space. We can reduce our search space to the upper half of our store or a list, because now we know that we can afford these 4 items on the left. We can afford the Scotch tape, we can afford the mug, the cap, the cookbook. Because we can afford the cookbook, then we can afford everything cheaper than it. And so now our new search space is all the expensive items. And we go to approximate middle, go do our check again. And this time we get a no, which means we reduce our search space to just the gaming headset, because everything more expensive than the Microsoft Office subscription is something we can't afford. And so now our search space is just this. We do our final check, and then it's good. So now we have figured out our most expensive item again. And notice, we essentially only have to do 3 checks for 8 items, which is a lot more efficient than doing at most 8 checks for 8 items, or average of 4. When you scale this up to 1,000, 100,000, a million, a billion different items, binary search becomes way more powerful. And so here's the pseudocode for binary search. You want to repeat this until your search space size is 0. Whatever search space you have, you calculate the middle point of it, And if the middle point is what you're looking for, then you should stop. Otherwise, if what you're looking for is less than what's at the middle, then you want to change your endpoint to be just less than the middle point. So you're essentially having your search space to the lower half of it. Otherwise, if what you're looking for is greater than what's at the middle, you want to change your start point to be just greater than the middle point. So you're essentially now just looking at the upper half of your search space. And then the runtime for n items would be O of log 2n, which is just, we would just write that as O of log of n, because you're dividing your search space in half each time. Notice we had 8 items, and then we only have to do 3 checks, which is, and what is log 2 of 8 is 3. I think that's good. All right. And so this is a really good search algorithm, but notice that your entire search space has to follow like what I call the binary search observation for this to work, which isn't really like something I can define. So instead, we're going to do a little quiz on it. This might not be what you expected, but I'm just going to hand you a problem, and I'm going to ask you guys if we can use binary search to solve it, and what, and if so, why. Okay, so if you tell me a time in like minutes and seconds, and I can tell you if I've run a 1 mile faster than that time, and I'll give you a hint, it's definitely faster than 20 minutes. And I want you guys to find out my fastest mile time. Is this something we can solve using binary search? Okay, you guys are nodding your heads yes. Could someone sort of explain why? Yeah. Mm-hmm. Yep, we can definitely use binary search to solve this problem. And basically what you said, if I can't run a mile faster than 10 minutes, then I can't run a mile faster than 9:59, 9:58, 9:57. So what does that mean? You can reduce your search space to 10:01 to 19:59. But if I can run a mile faster than 10 minutes, then I can run a mile faster than 10:01, 10:02, 10:03, all the way up to 20 minutes. And we reduced our search space to like 1 second to 9:59. And see, in both cases, we reduced our search space by half, and therefore we can run binary search on that problem. This is pretty much a similar problem. Tell me any day, and I'll tell you the number of Academy Awards actor Leonardo DiCaprio has on that date, and find the first day DiCaprio won his first award. These were all ideas that I was coming up with before the Brown card one, so I just added them all into a quiz. So can we solve this problem with binary search? We got a few no's. We got 1 yes so far. Okay, you want to explain like your answer? Yep, good job. So yes, you can use binary search to solve this problem. And it's essentially what you said. If Leonardo has 0 awards today, then he'll have 0 awards every day before today. And you can reduce your search space to every day after today. For pretend today is just, I say today, but I probably should have put like a specific date. If Leo has at least 1 award today, then he'll have at least 1 award every day after today. You can reduce your search space to every day before today. And then you reduce your search space by half each time, like whatever you set your bounds to. Like you can set it to the present date, to, I don't know, the day, or the day Leonardo was born to, I guess, today. Those could be your bounds. And then you could reduce your search space by half every time. So yes, you can use binary search to solve this problem. One last problem. This one's pretty easy. Given an integer array A of size n and a target number t, tell me if t is an A. This is probably what you guys were expecting for like me to start off with in a binary search lesson. So can we solve this with binary search? Yeah. Yep, good job. It's a yes if the array is sorted. And for those of you that don't know like why, it's because when the array is sorted, you can make a binary search observation. For some integer k, if k of k is less than t, then a of 0 all the way to a of k minus 1 is also less than t. You reduce your search space to a of k plus 1 all the way to the end. And if a of k is greater than t, then a of k plus 1 and everything after that is also greater than t. You reduce your search space to 0 to a of k minus 1. Again, then every time you reduce your search space in half, that means you can do binary search on it. So I think everyone here has like a decent grasp of like when can and when should we use binary search as opposed to linear search. So, oh, I thought we were going to go into a problem. I guess we're going to do a little demo for those of you that want the code that want to see like binary search in action or want like specific C++ code for it. You might, if for those of you in CS31, I'm not saying this is going to be on the second midterm if you guys have taken it, but there was code very similar to this on my second midterm. Just throwing that out there. I don't know if it was the same for you. You don't remember? Have you guys taken your second midterm yet? Oh, you guys don't have a second midterm? We had, for 31, I had two midterms. 2 weeks? Okay, well, you might have to read binary search or something like that. That's how Smallberg, I think, introduced it, which is kind of interesting. Anyway, we have a sorted array here, and we're just gonna do we're just gonna go through and just read the code. So our target is 19. Okay. We get to our first two statements that just sets like our endpoints, or start and end. First one's going to be 0, then size minus 1 is going to be 14. And we go into the loop. We go into the loop, we calculate the middle, which will be 7. What's in 7? It's 15. 15 is less than 9, or 19 is greater than 15. So we set our starting point to right after the middle, which is going to be index 8. We calculate the middle again. So the middle of 8 and 14 will be 11. 23 or 19 is less than 23. So our endpoint now goes right before the middle, which is going to be index 10. And we calculate the middle one last time. Middle of 8 and 10 is 9. What's in 9? That's 19, which is exactly what we're looking for. So we return our index, which is 9. Little demo code and like some starter code for the problems you're gonna have for the examples. And now let's move on to our first problem. So here's the link for you guys. It takes you to the like example contest. And I want you guys to think about like the solution, think about the problem, the solution to this, to guess the number, and maybe code it out if you have time. How many minutes should we give them? 5 minutes? All right. You guys will have like 5 minutes to look at this problem. So This is an interactive problem, which is a pretty weird problem. You're not going to encounter a whole lot in your like Caddis career, but just so you guys know, it's essentially your program is going to be talking with Caddis, and it does that by doing like printing the standard output. So in C++, that would be doing like C out. And then you're going to get a response back from Caddis. And this is like an example response. And essentially you want to take that through like standard input. So in C++, you would do that with a C in. And so the solution to this problem is essentially, I mean, no surprise, it's binary search. We could do linear search guessing from 1 to 1,000, but we only get 10 guesses, so it's not going to work for most cases. We can make the observation, though, that if we guess n and get lower as a response, then all numbers n up to 1,000 can't be the correct answer. If we guess n and we get higher as a response, then 0 all the way up to n can't be the correct answer. There's 2 B's right there. Whoops. And therefore, you can reduce your search space in half. If you start off with like the midpoint, so 500, you would reduce your search space in half. And you keep doing that. Essentially, you're just doing binary search to get the correct answer. And here is just solution code. You might take a look at this because this is how you do interactive problems. It's kind of weird. So I just start off with like our upper and lower bound, so 1 in 1,000. And while like low is greater than high, our guess is just going to be the middle number that we like output to Caddis, like to standard output. We're going to get a response back, so we take in a response, and then we see, is that response lower? Then what do? We're going to do high equals guess minus 1. So we're just going to search the lower half of our search space. If it's higher, then we're going to search the top half. And then else, we're going to get just, it's going to be correct. And then we can just end. And so we just do a break. Does this solution code make sense to everyone? Yep. Okay, one more problem. This is a bit of an application of binary search. It's going to be a little tougher finding out like where you'd actually use it in this problem. But I'll give you guys a few extra minutes for this problem. Just take a look at it, and if you have any questions, let me know. Okay, that's my cue. So hopefully you guys have had like a little bit of time to think about what this possible solution could be. We're gonna go over it right now. Okay, first we're just gonna, for those of you that like had trouble understanding like the problem, we're looking for the largest number H, such that there are H papers with at least H citations. So for our sample input 1, we have, our first number is 5, which means there's 5 papers. And then each of the next 5 numbers is the number of citations per paper. And so we have 7, 1, 2, 1, 5. There are at least 2 papers with at least 2 citations. So we have 7, 2, and 5 have at least 2 citations. But there aren't 3 papers with at least 3 citations. So that means our H index is going to be 2. And so we output 2 for this case. Next slide. Okay. For this example, we just changed 2 to a 3. And now there are at least 3 papers with 3 citations. It's going to be 7, 3, and 5. But there aren't 4 papers with at least 4 citations. So that means the largest number, like H, such that there are H papers with H citations, is 3. We output 3. One last example. For this one, there's 4 papers with at least 4 citations, which is just all the numbers. So 103, 104, 12, and 38. So there aren't 5 papers, and 4 satisfies our criteria, so we output 4. Anyone have like any questions on like what exactly we're trying to find? Okay, cool. Did anyone come, just wondering, did anyone like come up with a way to use binary search on this problem? Yep, that is actually the alternate solution. That's what Michael coded up here like just now. But I'm gonna try and go over like a sort of non-intuitive. The way that you were going for, I think, involved like two different binary searches. This one involves one, which I found to be like, this is the first one that I came up with, so I'm just gonna go over this one. So for this one, we're actually going to do binary search over the potential H index number. So our upper and lower bounds is 0 through n. And what we're gonna do is, starting from 0, we're gonna check, is 0 like a possible H index number? If it is, you go to 1, check if that one's a possible H index number, 2, 3, 4, all the way up to n. And let's say we get to 5 and it's like there aren't like 5 papers with 5 citations, then we know that our H index is 4. And that's essentially the linear like approach to it, like going from 0 all the way up to n. We could do linear search for that one, but unfortunately that takes too much time. When the numbers are really big and you submit this into Caddis, you're gonna get like a time limit exceeded error. Yeah, so we could do linear search from 0 to n, but that takes too much time. So we can make a linear binary search observation, luckily. We're looking for the largest number H, so that there are 8 papers with 8 citations. For some number K, if there are K papers with at least K citations, then 0 to K minus 1 can't be the H index, because the H index is, you're looking for like the largest number that satisfies this. And if K satisfies it, then yeah, 0 through K minus 1 can't be the H index. Any like questions on that? Or does that make sense? Okay, I got a few nods, so. But if there aren't K papers with at least K citations, then every number after it and up to n, so K plus 1 all the way up to n, can't be the H index. Because if there aren't K papers with K citations, then there can't be K plus 1 papers with at least K plus 1 citations. And so what does that mean? We can do binary search. Why is this not working? Okay. We can do binary search on the potential H index numbers, like again, starting with 0 and then going all the way up to n. We take the middle number and then we use our binary search observation to essentially reduce our search space, eventually finding like the largest like number that satisfies the criteria, which is going to be the H index. And so what does the code for this look like? Oh, wait, one more thing. How do we check if K is a potential H index? So how can we check if there are K papers with at least K citations? Oh, there's a few answers to this. We're just gonna go with like the simple one. We're just gonna use a loop and count the number of papers with at least K citations. So this is just the loop. So I just set like a count starting at 0, like a for loop, like going through like the n citation numbers. And paper citations, let's just assume that that contains like the number of citations for each paper. So if that is greater than or equal to K, then we just increment count. And then by the end of this for loop, we should have like the count, and then we can use that to compare with K. Yeah. Yep, that's also a good solution. I'm not sure if you'd want to do that for like every single time you do a binary search check, because that's like a n log n, like searching is n log n. Just a simple for loop would be O of n. But if you sorted like beforehand, that could that could also work too. So multiple solutions for this. This is the final code that I wrote out. So in this first little block here, I just get the first number, which is like the number of papers. So I do C and N, and then I create a vector called C, which has a size of N, and put all the number of citations in there. And then I set upper and lower bound, high and low. I have an H index. Essentially, I'm saving like the H index, like latest H index candidate by the end of the binary search that will have the H index in there. And then you've seen this code like 3 different times. It's just the while low is greater than high. I get the middle point where there's this comment right there. I just put in like my little for loop. You could also like do the sorted way that you were talking about. That would also work. You could also put in there. And then see, you're getting your count, like how many papers have like at least this many citations, like mid citations. And if count is greater than mid, then you have a potential H index number. You add that into H, like the H index variable, and then you set your bounds again. So then if you do have like a potential candidate, then you go check the upper half of your search space. Otherwise, you check the lower half of your search space. And then by the end of this, I forgot to do a C out for H index, but just pretend like that's at the end there. You just do C out H index, and then that'll be your answer. So does anyone have any questions for this problem? This is like a foundation. This is essentially like the template problem for like all the following contest problems. So make sure you understand this one well. But if there aren't any questions, we are basically wrapped up with this presentation. So if you guys have any like further questions, any comments or concerns, don't forget to fill out our feedback form. If you don't, still fill out the feedback form. Thanks to ACM Design for creating this neat looking Bruin card with Powcat on it. If you're interested in like designing graphics like this, then go check out design events. I would say like apply to be an intern, but I think that deadline's already passed, so oh well. But yeah, thank you guys all for coming. Here is the contest link. I encourage you guys to work together for this because these problems are pretty tough. Binary search is actually a pretty tough concept, especially when you apply it into like competitive programming. So you guys are like sitting together in groups. I really like that. Work together on these problems. And yeah, that's all there is for me. Thank you, everybody.